Hello everyone, first year university students who are doing mathematics. So today I would like to take you through a mathematical concept called integral calculus. I'll be dwelling so much in the introduction to integration. So if you find this video interesting, like, subscribe and share. Support me by liking, subscribing and sharing my videos. So I will take you through lecture 1, which is integral calculus, integration. So in the first semester, you dealt with derivatives of a function. So this integration go hand in hand with differentiation. This time around, we consider the inverse problem. For instance, given the derivative of an unknown function and seeking to find the original function itself. So that means we'll be given a known derivative of a function and all we'll be wanting to find is the original function itself. So let's deal with entire derivatives. So let's start with an entire derivatives or antiderivatives. So what is an antiderivative? Definition. So a function f is an antiderivative of a function f. So these two functions, they differ by cases. The antiderivative one is the uppercase and the original function is a lowercase. So a function f is an antiderivative of a function f on an open interval bounded with the lower limit a and upper limit b. So a function f is an antiderivative of a function f on an open interval ab if f prime of x is equals to f of x. So it is said to be an antiderivative if f prime of x is equals to f of x, but for all f of x inside the interval ab. So it means that we say that a function f is an antiderivative of a function f if we derivate that entire derivative and we get the original function for all x inside an interval. So for an example, we can look at example. For an example, we have f of x equals to x to the power 5 and h of x equals to x to the power 5 minus e to the power 9 and g of x equals to constant c plus x to the power 5. These are all an antiderivatives of f of x equals to 5x to the power 4 for all x belonging to real number. Why? This is because if you can derivate this guy, you get 5x to the power 4. If you can derivate this guy, you get 5x to the power 4. This is the derivative of a constant which is minus 0, which is just 5x to the power 4. So if you derivate this guy, g of x equals to c plus, this is a constant, it goes to 0 plus 5x to the power 4, which is 5x to the power 4. So it means that they are all antiderivatives of that, since the f prime of x, h prime of x, g prime of x is equals to f of x is equals to 5x to the power 4. So take note that antiderivatives are not unique. They are not unique, so you are free to add a constant because the derivative of a constant is 0. So you are free to add any constant because these antiderivatives, they are not unique. So let's go to the first theorem. The theorem says let y equals to f of x be an antiderivative. So if you let y equals to f of x be an antiderivative of y equals to f of x on an open interval ab, then every other antiderivative of f on ab is of the form y equals to f of x plus c for some constant c. That means if you let y of f of x maybe be an entire derivative of y equals to f of x on an interval ab, then every other antiderivative of f is of the form y equals to f of x plus c. That means we need to add a constant. So that's what all this theorem is saying. So we can go to the table of functions and their general antiderivatives. So this table is just showing the functions and their general antiderivatives. So let's go. Functions, as you can see, and their general antiderivatives. So first function, a function x to the power n, where n is an integer. So to find its antiderivative, we say x to the power n plus 1. That means in the exponent we add 1 and we divide by that exponent, which is n plus 1. But this is provided that n is not equals to minus 1, because if n is equivalent to minus 1, then in the denominator we will have minus 1 plus 1, which is 0, which is a taboo in mathematics to do that. So that's how we find the general antiderivative of a simple function x to the power n. So second function is a trigonometric function sine. Sine k of x, a k is any constant and x is a variable. So sine k of x, so how do we find the antiderivatives of such function? So in other words, in antiderivatives, we ask ourselves that what do we differentiate to get sine k times x? So you know that we differentiate cos of k of x to get, we differentiate negative, of cos of k of x to get sine k of x, because generally cos of k of x, its derivative is negative side. So to have positive, we must have negative cos k of k times x. So because when we differentiate, we make use of the chain rule, we will differentiate also this part, which will be k. That means we should have 1 over k this side. That's why the antiderivative of sine kx is nothing but negative 1 over k cos kx plus c. Don't forget that we proposed the theorem to say that antiderivatives are not unique, so we are free to add a constant. One can say k, y can say g, whatsoever, as long as we add a constant. So that's why sine kx, its general antiderivatives is minus 1 over k cos kx plus a constant c. So we also have got a trigonometric ratio of function cos kx. So similarly, we do the same thing. We ask ourselves, what do we differentiate to get cos? So obviously sine. So then because we will be using a chain rule where it will be k sine of something, that means we must have what called the reciprocal of that k, which is 1 over k. So that's why the cos kx, its general antiderivative, it's 1 over k sine kx plus a constant. So we also have got sec squared kx. So we ask ourselves again, what do we differentiate to get sec squared of x? Obviously it's tan of something. So that's why we have tan kx. Because we'll be making use of the chain rule, we must have the reciprocal of that k, which is just 1 over k tan kx plus a constant c. So when you go to the cosec squared kx, we know that we differentiate cot to get cosec squared x. That means negative 1 over k cot kx plus c is the entire derivative of cosec squared x, because when we differentiate these 1 minus 1 over k cot k times x, we get the what? We get the function or the original function as the definition stated. So number 6 is the entire derivative of sec k times x plus sec kx times tan kx. which is equals to 1 over k sec kx plus a constant, because when we differentiate sec x we get this guy. So this 1 over k is from the reciprocal of k, because we make use of the chain rule. So we also have got what we call number 7, which is cosec kx times cot kx. You know that if we differentiate cosec of something kx, we'll get obviously cosec kx times cot kx. So we differentiate this guy to get this guy. So minus 1 over k is the fact that when we differentiate cosec, we get negative cosec kx times cot kx. So to have it positive, we need to have negative again of minus 1 over k times cosec kx plus a certain constant. So that's what is happening. So we also have a derivative of a function 1 over x. So the derivative of a function 1 over x, it's nothing but ln of the absolute value of x plus a constant. So that's another rule, or that's how we find the entire derivative of a function 1 over x. So the entire derivative of a natural exponential function e to the power x is quite simple, because you will remember that when we differentiate e to the power x, we get e to the power x. So when we differentiate e to the power x, we get e to the power x. So we ask ourselves that what do we differentiate to get e to the power x? Obviously, the integral of e to the power x dx is nothing but e to the power x plus a certain constant. So that's why we have this guy e to the power x plus a certain constant. So we can go to number 10, which is the entire derivative, or second entire derivative of a what to call this exponential function. So this is any exponential function. B is any number, so any real number. So to do that, we have b to the power x over ln of b plus c. So this is how we find the general antiderivative of a function, of an exponential function b to the power x. If we can take for an example, we can talk about 2 to the power x, or let me say we can talk about what to call f of x equals to 2 to the power x. So its antiderivative will be 2x over ln of 2 plus a certain constant. So this is an example. So that's how we do it. So that's normally how we do it. So we can move to some examples and the solutions to show you how do we indeed apply these rules. So yeah, examples. So the question says find the antiderivatives of the following problems. So we have the first problem, which is f of x equals to x to the power minus 5, g of x equals to e to the power 5 plus pi, h of x equals to 1 over e to the power x, dt of x equals to 2 over square root of x, and e equals to is r of x equals to cos 2x, and the last one is f, which is p of x equals to sine a of x over e. So how do we go through this? You know that this first one, we're making use of the first rule in the table. So what we are doing here is nothing but to make use of that rule, saying if we've got f of x if we have f of x equals to x to the power n, its entire derivative will be x n plus 1 over n plus 1 plus c. So what we have here is f of x equals to x to the power minus 5. It means that to find its entire derivative, we'll say x, and in the exponent we have minus 5 plus 1 divided by that exponent, which is minus 5 plus 1. That's the base. We're using that first rule. So this will be this following is a simplification, is x to the power minus 4 over minus 4, which is just equal to minus 1 over 4 x to the power 4, because this one is x, it's 1 over x to the power 4 just times 1 over minus 4, which is just equal to minus 1 over 4 x to the power 4, then plus a constant. So that's how we do number A. So we have number B. Number B is a constant. If you can see, number B is number B is a constant. So e to the power 5 plus pi, they are constants, they are numbers. So we differentiate, if we have f of x equals to 2 and we want to find its entire derivative, its entire derivative would be simply 2x, because when we differentiate this we get 2. It means that g of x, its entire derivative will be capital letter G into e to the power 5 plus pi x plus a constant. That's how simple we do it. So we also have number C, which is h of x equals to 1 over e to the power x. So you know that 1 over e to the power x can be simplified to be e to the power minus x. I discussed about this one, that its derivative, it doesn't change. This will simply be negative e to the power minus x plus c. So what about this number D? Number D is t of x equals to 2 over square root of x, but we can simplify this to be 2 into x if we write this one into power. So it will be x to the power 1 over 2, and this one can also be written as 2x minus 1 over 2. So then that means we're using the first rule, where we're just saying 2, here we're adding 1, and we're dividing by this one plus 1. We undergo simplification to be 2x, then minus 1 over 2 plus 1 is 1 over 2 over 1 over 2, which is just a 2x 1 over 2 times 2. So divide changes into multiplication, then we interchange denominator and numerator. So this will be 4, x to the power 1 over 2 is just square root of x. So that's how we do this one. So then number E, it's Rx equals to cos 2x. What do we differentiate to get cos? We differentiate sine. So it means this will be sine 2x. Because we'll be using chain rule, we must have 1 over 2 times sine 2x, but plus a constant. You must not forget a constant. So number F is a simple thing like these p of x equals to sine x to the power e. So what do we differentiate to get sine? Obvious, we must have cos. So sorry, there is a mistake. Obvious, we must have what to call p of x equals to cos first. We differentiate cos, because when you differentiate cos we get negative. We must have negative. We must have negative cos. But because we're going to make use of the chain rule, that means we will have 1 over e, negative 1 over e. No, it will be e, sorry. It will be e, not negative. it will be negative e times cos x over e plus a certain constant. That's how simple we'll do it. So we first seeking to know what to differentiate to get sine. It's cos but negative, because when you differentiate cos of x you get negative sine x, so it should be negative cos, because when you differentiate cos you get negative sine. But because we're going to make use of the chain rule, that's why we must consider this part also, because when you differentiate this part we got 1 over e, so we must have the reciprocal of 1 over e, which is e. Thus this one will be negative e cos x over e plus c. So this comes to the end of our section, to the end of our session. So thank you very much for being with me. So don't forget to support me by liking, subscribing and sharing my videos. Thank you so much. We'll meet in the next lecture.